Hello everyone and welcome to lecture today. What I want to talk about today is Fubini's theorem, both for rectangular domains and in general. So to start off today, what we're going to do is talk about, I'm going to kind of remember how to integrate over a rectangular domain. So recall that when we integrate over a rectangular domain, so integrating and we'll call it R. We can call this the x coordinate goes from A to B for constant real numbers A and B, and the y coordinate goes from C to D for the y coordinate C to D. If we want to draw a picture of this, we can go ahead and do that. We can kind of say, in general, this is our x-axis and our y-axis. Our domain, if x goes from A to B and y goes from C to D, is going to look like this. So the region R, if it's a rectangular domain, looks exactly like this. And typically what we're interested in is integrating a function, f of x, y, that's defined for points in that region. So we talked earlier about how a function of this form, or for a function of this form over a rectangular domain, the double integral over R of the function f of x, y gives us the accumulation of that function inside the region R, and we can evaluate it by doing what's called the iterated integral, or the 2 times we integrate. Specifically, we take the function f of x, y, and we do the y integral first, the integral from C to D. And whatever that gives us, it'll be a function of x once we do the y integral, which we can then do, again, the x integral from A to B. Now, Fubini's theorem for a rectangular domain is very, very nice. And it's relatively simple. What it says is that this equality right here is due to what's called Fubini's theorem. For rectangular domains. It says that the order of integration doesn't matter. We can integrate with respect to y first and then with respect to x, or instead we could consider the double integral of the function f of x, y dx dy, where x is going from A to B and y is going from C to D. So Fubini's theorem for rectangular domain says that we can always do this. For any rectangular domain, we can just very, very quickly switch the order of integration, and this value that we get from integrating with respect to y first and then with respect to x is going to be the same value that we get for doing the integral with respect to x first and then with respect to y. A good idea is to test this out, so I really recommend that you test this out for a couple different examples. So for instance, you can take any of the web work problems 1 to 5. Each one of those, I believe, has a rectangular domain, and if you switch the order of integration and go through with that in the new order of integration, you should get the same value for the answer that you got when you went through and you did the opposite order, the y dy dx order. So the question that we want to answer now is, and we kind of talked about this a little bit last class, is how to integrate over general domains. We'll put more general domains. So for example, if we can kind of draw a picture of a slightly more general domain in the following way. This is very much related to when we went through the other day and got the area of a circle. But a more general domain is going to be something that is bounded above and below by A and B and X, and above and below by C and D and Y. And maybe has a shape that looks sort of like this. So the idea then is, and this is kind of, again, very, very related to how we did it for the finding the correct bounds of the integral on the circle. We want to split the domain here up into two pieces. And the formula that we get when we do that is exactly the following. It's always going to be of the form of an iterated integral, the double integral over R of some function f of x, y. This is going to be an iterated integral of the same function, but we have to choose an order. So in this case we'll do dy dx, and then we have to figure out what the new bounds are going to be. So the idea is that we take our domain. This is our domain R right here, and we split it into two parts. In this case, because x is our outer integral, x is always going from the minimum part of the domain, in this case A right here, to B right here. So your outer integral is always going to be from a constant to a constant. In this case, from A to B. But just like we saw in the circle example, the upper boundary and the lower boundary for y is changing as x changes. So for instance, if I go to this point right here, x, along the x-axis, my lower boundary for y is actually this point right here. It's definitely not 0. And then concurrently, my upper boundary at that point x is right here, which is not the same thing as d. My upper boundary is definitely not d there. It's lower than d. It's only d at this point right here. So what we do is we typically say that, well, for our domain R, after we've split it to a top part and a bottom part, our upper boundary will be given by some function of x. For the notes, I'll call it h of x. So let's say that this upper curve right here, we call it, it'll be y equals h of x for some function x. And the lower boundary is given by y equals, we'll say, g of x for some other function x. That's our lower boundary. Which means that as x kind of slides from A to B, the lower boundary is governed by g of x, and the upper boundary is governed by h of x. So that's what our lower and upper bounds are going to be in the integral when we integrate. We're going from a lower bound of g of x, whatever that is, at any x value, up to an upper bound of h of x. And this is the general way now that we have of integrating over a more general domain. We can consider even more general domains than this shape right here. Not all domains have this nice function on the top and function on the bottom, but in some sense this isn't that big of an issue, because even if the domain is more complicated, like say it looks like this, we can always cut this domain up into smaller pieces, and each one of those pieces is going to obey, it's going to be governed by a top half and a bottom half, or a left half and a right half. So for instance, for this domain, you kind of think about a cut right here, and then a cut right here, a cut right here, and then a cut right here. So the integral over this domain is going to be integral over R1, R2, R3, R4, and R5. Each one of these smaller domains has a shape like this, so we can evaluate the integral over each one of these subdomains, and then just by additivity, which is our fourth property in the nice properties of integrals that we talked about the other day, we can just add all those results up to get the total integral over this region R. So this is a very, very flexible idea. Let's do an example. The first example that I want to consider today will be the double integral of, it'll be polynomial and an exponential function kind of multiplied together. So we'll say the integral from 0 to 1 in x, and from 0 to x squared in y. We'll do the function 3x cubed e to the x times y, dy dx. You always want to draw a picture, and we're going to see that's even more important when we start talking about how to change the order of integration for multiple integrals. So what is this domain? This domain is saying go from 0 to 1 in x. Then as x goes from 0 to 1, the lower boundary in y is 0, so there's the x-axis, and the upper boundary in y is the function y equals x squared. So at 1, x squared is equal to 1, or 1 squared is equal to 1. So this is what the upper boundary is at this point, and at 0 it's this right here, and then all along the x-axis the lower boundary is 0 for y, and the upper boundary is the curve y equals x squared. And so our region, at any point, this is the lower bound and this is the upper bound, at any point along the x-axis, the region that we're integrating over becomes this region right here, this region R. So the value of this integration, when we go through and do it, is going to be the accumulation of this function, this is our f of xy, inside this region R. So going through and doing our iterated integral procedure ends up giving us the following. 3x squared doesn't depend on y at all, so because it's constant with respect to y, we can factor that out of the integration, or 3x cubed. And then we have the antiderivative from 0 to x squared of the function e to the xy dy. Remember, we do the inner integral first. So this antiderivative of of e to the xy is 1 over x e to the xy. This is evaluated from x squared to 0. And when we plug in for y, because remember we're plugging in here for y, this becomes the integral from 0 to 1 of 3x cubed. And actually, x cubed over x is just x squared, so we'll simplify that right away. It becomes e to then we plug in x squared for y, we get x cubed. minus e to the x times 0, which is just e to the 0 or 1 dx. So this is now a single variable integral from Calc 2. So we can use all of our rules from Calc 2 for single integrals. And I think the easiest way of looking at this is looking at this as the integral from 0 to 1 of 3 times x squared e to the x cubed dx minus the integral from 0 to 1 of just 3x squared dx. This integral right here we can get through the use of a u substitution. I do u equals x cubed. And if we do that, then du is going to be 3x squared dx, which is exactly what we have here in the integral symbol, or in the integral. So this becomes then just the integral from, and then this is going to be, when x is 0, u is 0, so the lower bound in u is 0. And when x is 1, u is 1 cubed, so the upper bound is also 1. So the function e to the u du minus the antiderivative of 3x squared dx, which is 3 times antiderivative of x squared is x cubed over 3. We need to remember to evaluate that from 1 to 0. Because we're doing the fundamental theorem of calculus here. This entire thing then is the antiderivative of e to the u is just e to the u. The 3 over 3 becomes 1. So we're just left with here, when I plug in the bounds for this antiderivative, we have 1 cubed, which is 1, minus 0 cubed, which is 0. And lastly, when we plug in for e to the u here, we have e to the 1 minus e to the 0. That's just e to the 0 is 1, so our final answer is e to the 1 minus 2. And this value is the double integral of this function over this region right here. It's approximately equal to 0.718. I'll put out a little 718282. So a good question to ask is whether or not Fubini's theorem holds in general. And it turns out it does, which is very, very, very cool. We'll see, it's an extremely useful tool for us in terms of integrating functions of multiple variables. Specifically, I'll do an example a little bit later on that shows even functions that don't appear to be integrable can sometimes be integrable. And we can get a nice result just by switching the order of integration. For certain integrals, we'll actually see that if you try and do the integral in a specific order of integration, like dy dx, that order won't be correct. It won't actually work out nicely. It'll be hard, if not impossible, to get the integral in the order dy dx. But if we switch the order of integration, we can sometimes get a nicer integral to evaluate that comes out to a much more analytical, nice answer. So I guess the main thing to remember here is that Fubini's theorem still holds for general domains. I'm going to put a big however. we must be very careful. I'm going to underline it 3 times. So the general idea is going to use that the image that we had before of the general domain. So I'm going to just kind of copy this and bring it down and kind of use this same image. And what we're going to do is we're going to erase, not the domain, we're going to erase a couple of the points. So that point, and we'll erase y equals h of x. We'll erase this as well. And the idea here is, so if before we had that the integral, the double integral over r of f of xy dA was the integral from a to b of the integral from, I think was the lower bound was h of x, or g of x, the upper bound was h of x. So g of x to h of x of the function f of xy dy dx how can we figure out the new bounds of the function of the integral of the function f of xy dx dy? And the idea is very, very similar to before. Well, the outer bound has to be a constant to a constant. So if we draw a line from C to D, where C is the bottom of our domain to the top of our domain, this gives us the direct new bounds for y. It's from C to D. But now what we have to do is go through and kind of split our domain again into 2 pieces, where the top of the domain, in this case now, the top of the domain corresponds to the left side of this blue line, and the bottom side of this domain corresponds to the right side of this blue line. What we need to be able to do is figure out how to express now this curve right here, the right half of the domain, or the upper part of this domain now, upper with respect to the x-axis. So the upper part of this domain as a function of y. So let's say this curve right here is the curve x equals w of y for some function w, and we also need to be able to express the lower bound of this domain as some function v of y. So x equals v of y, which is w and v. And what that means then is that as we go from C to D, or as we go in y from C to D, at any given specific y value, the lower bound is given by v of y, which is this function, and correspondingly the upper bound is going to be given by the point w of y, which is straight across. This is the upper bound in the domain. So if you consider kind of like this line, or this straight line right here sliding from C to D, the upper bound and the lower bound on a general domain are changing as these specific functions. So v of y right here, and then w of y right here. And this is the correct way of doing Fubini's theorem. Fubini's theorem for a general domain says that these two values, the value of the integral in the order dy dx is the same as the value of the integral in the order dx dy but you have to be careful with how you figure out these new functions w of y and v of y. So Fubini's theorem for general domains says that these two values are equal to one another. So to kind of summarize Fubini's theorem, it says that the order of integration doesn't matter, but the idea is that we have to be very, very careful with how we determine our bounds. If we are given an integral in one order on a general domain and you have to reverse the order of integration, determining these new bounds becomes, in general, a question of what these functions w of y and v of y are. In general, they're related to the inverse of the original two functions. They're not the same as, but they're related to the inverse of the boundary functions in the opposite order. So let's go through and do an example. And what we'll do is we'll take the example, we'll do the double integral, and x here will go from 0 to 9, or actually y will go from 0 to 9. And then from the curve x equals the square root of y to 3. And we'll integrate the function x plus y. And this is in the order, if you have a function of y here, it kind of implies that the order is going to be in the order dx dy. Because what this is saying is that y is going from 0 to 9, and then x is going from this function of y to whatever this function of y is, which for us is just 3, which is nice. In general, the upper and lower bounds can be a function of the outer variable. So you always want to draw a picture of this, so you kind of know exactly what you're dealing with, what shape this region is, what the region R is. All of the information that you need to determine that is in these bounds. It's contained in these bounds. So what we have here is that we'll kind of do, say this is 3, 6, and 9 for y. And if this is 3, then this is 3 for x. And we know that y is going from 0 to 9. And as y goes from 0 to 9, we're going in x from the curve square root of y to the upper bound of 3. So at 3, this is going to be my upper bound in x. And the lower bound is the square root of y. Well, the curve x equals the square root of y is the same thing as the curve y equals x squared. So it looks like this. At 3, when x is equal to 3, y is equal to 9, which is exactly what we expect. And then if our lower bound is this curve, then at any specific y value, say like right here, our lower bound is this curve, and our upper bound is x equals 3, which means that our domain is this space right here. All of the stuff underneath the parabola, x equals square root of y, or y equals x squared. So after doing this, now we have a good idea of what the domain of integration is, and it's this picture that we need to use to determine the new bounds if we were to switch this order of integration. But I do want to just go through at least once and show you that this is actually holding out really nice. And we'll use this example as our test example just to sort of test Fubini's theorem. So before we switch the bounds of integration, let's go through and actually figure out what this value should be. So is the integral from 0 to 9, and the antiderivative of x plus y with respect to x is x squared over 2 plus y times x. And this is evaluated at 3 as an upper bound and the lower bound of square root of y. And when we plug in, I plug in 3 here, I get 3 squared over 2, or 9 over 2, plus 3 times y. We have to subtract from that the square root of y being plugged in here for x. So it's the square root of y squared over 2, which is y over 2. And it's plus y times the square root of y, which is y to the 1/2. So going through and simplifying, you end up obtaining that this is the same thing. You just you do 3y minus y over 2, and then y times y to the 1/2 is y to the 3/2. This is the same thing as the integral from 0 to 9 of 9/2 plus 5/2 times y minus y to the 3/2 dy. And this integral is a single variable integral, so we can go through and integrate each one of these terms to get 9/2 times y for the antiderivative of 9/2, and then it'll be plus 5/4 times y squared, because the antiderivative of y is y squared over 2. And then lastly, you could use the power rule on this, so it becomes 1 over 3/2 plus 1 times y to the 3/2 plus 1, or after a little bit of simplification, 2/5 y to the 5/2. This is evaluated from upper bound of 9 to a lower bound of 0. So our final value ends up becoming exactly, when we plug in here, when we plug in for 9 and then plug in for 0, when you plug in for 0, everything here is 0. So it just becomes, it'll be 9 squared over 2 plus 5 times 9 squared over 4 minus 2 times 9 to the 5/2 over 5. And you can take this just in arithmetically, it simplifies down to this number is the same thing as 891 over 20, which is 44.55. So this is the value of this double integral. And what I want to do right now is go through and show you that if we correctly switch the order of integration, we'll obtain the exact same value, courtesy of Fubini's theorem. You can call him the Great Fubini. It sounds kind of like Houdini. So we're going to have that the new order of integration is going to be dy dx. And what we want to do is determine what our new bounds are going to be for this integral. And I want to emphasize again that it's not just like a rectangular integral. It's not as simple as just switching these two integral signs. We have to look at this domain and ask ourselves what the new order is going to be. Remember, what we're looking for is first getting our outer bounds, which are for x. And what you can see is that this region goes from x equals 0, which is right here, to x equals 3, which is right here. So the bounds for x are going to be from 0 to 3. And then as x goes from 0 to 3 in this region, the y value goes from a lower bound of right here, which is y equals 0. So our lower bound is just going to be y equals 0. And our upper bound is going to be not 9, but given by right here. So for any point on this curve right here, the upper bound, any point x, the lower bound is going to be 0, and the upper bound is going to be governed by the points on the curve y equals x squared. Which means that our upper bound is going to be x squared. What that's saying is that as x goes from 0 to 3, our lower bound is staying constant at 0 for y, but the upper bound is a function of x. It's the function x squared. So these are the correct new bounds, and with these new bounds, we end up going through and we got to do our iterated integral procedure, which is we do the y antiderivative first. So it turns out that we do y first, and this is the antiderivative of x with respect to y is just y. And the antiderivative of y with respect to y is y squared over 2. And we have to plug in our bounds, which is x squared and 0. So when we plug in our bounds, this is actually a nice simplification compared to the previous integral. So our lower bound here is 0. So when I plug 0 in for y squared and y, I'm going to get 0. Which means that all I have to really worry about is this upper bound. When I plug that in, I get x squared times x, which is x cubed. Then I get x squared squared over 2, which is x to the 4th over 2. This is the dx. Oops, let me change that. It shouldn't be dy right there. It should be dx. And hopefully you can already see that this order of integration is actually giving us a simpler integral to evaluate compared to the original order of integration. It's not that much simpler, but it's a little bit simpler. We only have 2 terms here, and they're actually nice powers instead of this 3/2 right here. So this is actually a relatively common thing where one order of integration will give you a nicer second integral or outer integral to evaluate. So you want to be able to choose the better order of integration to kind of simplify calculation time. The antiderivative of x cubed is x to the 4th over 4. And the antiderivative of x to the 4th over 2 is x to the 5th over 5, which we have a 2 here, so it gives us 2 times 10. And we have to plug in here 3 and 0. So again, when x is 0, both x to the 4th and x to the 5th are 0. So really this is just going to be 3 to the 4th over 4 plus 3 to the 5th over 10, which not surprisingly will, when you bring this to common denominator and simplify everything, reduce to 891 over 20, or 44.55, which not surprisingly, due to the great Fubini, is the same value as the other integral that we calculated. I guess it's appropriate here to say thank you, great Fubini. So the last integral that I want to consider, and the last, I think, example that I want to consider shows that sometimes not only is it nice to switch bounds, the bounds of integration, sometimes you get an integral that is actually impossible to evaluate analytically by going through and doing it in a specific order. So sometimes if you have a specific function, a certain function that doesn't have a nice antiderivative, if you try and go through and do the double integral in one order, you won't be able to. You'll be forced to switch the order of integration, and that switching of the order of integration actually might make it possible to evaluate and get the exact value of the integral. So this next example is going to show that. Sometimes even switching the order of integration doesn't really help you much, but there are many examples of when you might be able to switch the order of integration and actually get an actual, a real number, an actual solution in one order, and in the other order not be able to get anything at all without using some sort of numerical procedure. So here the integral that we're going to evaluate is going to be the integral from 0 to 6, and from, we'll say, y over 2 to 3. And we'll do the function e to the negative x squared dx dy. So this domain is going from 0 to 6 in y. So I'll call this 3, I'll call this 6 right here. So if we're going from 0 to 6 in y, this is x, this is y. 0 to 6 in y, our lower bound is the curve x equals y over 2, and our upper bound is just the constant x value 3. So our region, we know then, is going to be, if our upper bound is the constant x equals 3, we're going to have this right here. And then if the lower bound is the curve y equals 2, or x equals y over 2, that's the line of slope 2 going up to that point right there, the point 3, 6. So what that gives us is that as y goes from 0 to 6, x goes from this line y over 2 to the constant value 3 at any point y. So the region that we're integrating over here is this triangle, this region R right here. So remember, this boundary right here, the lower boundary for this region in x, is the curve x equals y over 2. So the problem here is that if you try and go through and do this antiderivative of e to the negative x squared dx, you're going to run into an issue. The function e to the negative x squared is one example of a function who does not have a nice antiderivative. So there's no nice antiderivative of e to the negative x squared. This function is a very important function for a number of different reasons. It shows up a lot in probability and statistics, specifically when you're talking about the bell curve or the normal distribution. But the main issue for us here is that we can't evaluate this first integral using the fundamental theorem of calculus because there's no nice antiderivative of e to the negative x squared. The definite integral of the function does in fact exist, but there's no nice antiderivative of the function. In mathematical terms, we say that the antiderivative doesn't exist in closed form, which means expressible as nice functions, like transcendental functions and whatnot. So unfortunately, we're kind of at a loss here for how to get this double integral. But if you remember Fubini's theorem, we have a little bit of a hope that if we do Fubini's theorem and switch the order of integration, we'll be able to get the actual value of this integral. So I believe here would be an appropriate time to say, help us, great Fubini, you're our only hope. And if you didn't get that reference, that's okay. It's a Star Wars reference. So let's go through here and see if we can get this integral by switching the bounds of integration, the order of integration. The function that we're integrating stays the same when we switch the order of integration. But this new integral is going to be the integral in the order dy dx, or x as our outer bound and y as our inner bound. And we know that x goes from 0 to 3, or here to here, for this domain. And then what we need to do is look at how the y coordinate changes with respect to x. And it should be relatively apparent that the lower bound for y is exactly given right here. At any point, it's equal to 0. So our lower bound for y is 0. But our upper bound for y is changing. It's always going to be at any point x right here on this upper boundary curve, on this line. And the line in terms of x is x equals y over 2. In terms of y, it's y equals 2 times x. So our upper bound for y as we go from 0 to 3 in x is just going to be 2 times x. And now these are the new correct bounds for our integral in the reverse order. And what we notice is that this is the same thing as 0 to 3. E to the negative x squared is a function of x. So it's not dependent on y, which means it comes out of this integration. And, well, we can now at least do the inner integral with respect to y, because this is just the integral of the constant function 1. So this is just going to be the antiderivative of 1 with respect to y is y. Plugging in the top bound and the lower bound ends up giving us 2x minus 0. So what we're left with is that I is just equal to the integral from 0 to 3 of 2x e to the negative x squared. And this is now a single variable integral, and not only that, it's a single variable integral that we can in fact evaluate. And I'll let you think about that for a second. Why can we evaluate this integral when we couldn't evaluate the first function? And the whole reason here is because we have this x that appeared from the switching of the bounds. Right, this new integral, it's a single variable integral with an x and e to the negative x squared. You should recognize this as directly as an integral that we can do a u substitution on. If we do a u substitution of u is equal to x squared, then du is going to be 2x dx, which is what we have here. So this integral is now going to become the integral from 0, because x squared, or 0 squared, is 0. And then our upper bound is going to be 3 squared, so u at x equals 3 is going to be 9. And it's the function e to the negative u du, which is the antiderivative negative e to the negative u from 9 to 0. which is exactly equal to, when we plug in the upper bound and the lower bound, it'll end up being e to the 0 minus e to the negative 9. So we have a negative sign right here, so the order actually flips. And this now is just equal to 1 minus e to the negative 9, which is approximately equal to 0.9998765, and is the exact value of this integral, the integral of the function that originally we didn't think we'd be able to get a value for. So the idea here is that switching the bounds in general is often very, very important to actually be able to figure out the answer to a specific problem, a given problem. But thank you all for listening to the lecture today. We're pretty much done. If you have any questions, make sure to send me an email. But the next lecture will be on different coordinate systems and integrating using polar coordinates in 2D.